Master Terraform. Notes and real-world practices level up your infrastructure as code skills with concise notes. Practical examples: Siddhapa B, Senior Software Architect, Cloud&Devops, Tech Enthusiast, LinkedIn. LinkedIn 1. Terraform Guide. What is Terraform? Terraform is an IT infrastructure automation tool for building, changing and versioning infrastructure safely and efficiently. Terraform can manage existing as well as custom in-house solutions. It turns your infrastructure as code, i.e. your computing environment, has some of the same attributes as your application, and your infrastructure is version-able. B. Your infrastructure is reusable. C. Your infrastructure is testable. D. Minimizes errors and security violations. You only need to tell what the desired state should be, not how to achieve it. Terraform is cloud-agnostic. Features of Terraform: infrastructure as code. Infrastructure is described using a high-level configuration syntax. Cool. Provides single unified syntax. Executes plans. Terraform has a planning step where it generates an execution plan. The execution plan shows what Terraform will do before making the actual changes. Resource graph. Terraform builds a graph of all your resources and parallelizes the creation and modification of any non-dependent resources. Terraform builds infrastructure as efficiently as possible. Change automation. Complex change sets can be applied to your infrastructure with minimal human interaction. With the previously mentioned execution plan and resource graph, you know exactly what Terraform will change and in what order, avoiding many possible human errors. Terraform workflow and write. Infrastructure as code plan. Preview changes before applying. A. Apply. Provision reproducible infrastructure. 2. Terraform Guide. HCL. HashiCorp Configuration Language. Terraform code is written in a language called HCL in files with the extension. Terraform can also read JSON configurations that is named with the TFGS on. It is declarative language, so your goals is to describe the infrastructure you want, and Terraform will figure out how to create it. HCL syntax is composed of blocks that define a configuration in Terraform. J blocks are comprised of each value pairs. Single line comments start with %, multi-line are commented with dog and Joe Jason Joer, and double quotes. Boolean values. True, false. List values are made with square brackets. For example, foo bar, bars maps, can be made with braces, and colons, for example. Strings can interpolate other values using syntax wrapped in $. For example, $infrastructure as code, IAC. Tools like Terraform provide several key benefits. 1. Consistency and reproducibility eliminates human error. By defining infrastructure in code, you reduce the chances of errors that typically occur during manual configuration. Version control. Infrastructure configurations are stored in source control, for example Git, making it easy to track changes, roll back, and collaborate with teams. 2. Automation and efficiency. Automated provisioning. Terraform allows for the automated provisioning of resources across multiple cloud providers, reducing the time and effort required for manual setup. Repeatable deployments. You can easily spin up identical environments for different stages of development, for example, dev, staging, production. Ensuring consistency. 3. Scalability and flexibility. UL. Infrastructure scaling. With IAC, you can scale resources automatically based on changing needs by modifying the configuration and running Terraform. Apply to update the infrastructure. Multi-cloud support. Terraform supports multiple providers, Azure, Google Cloud, Kubernetes, etc., enabling a multi-cloud or hybrid infrastructure without vendor lock-in. 4. Collaboration and versioning. Through collaboration, teams can collaborate on infrastructure changes through pull requests and code reviews, enhancing team communication and workflows. Versioned infrastructure. By using version control, Changes to infrastructure can be tracked over time, and specific versions of infrastructure can be deployed. 3. Terraform Guide 5. Documentation to declarative configuration. The infrastructure code itself serves as documentation for how the system is set up and configured. This is much clearer and more up-to-date than manually written documentation. Easier onboarding. New team members can review the code to quickly understand how the infrastructure is set up. 6. Cost control. Cost management. With Terraform's ability to define and manage infrastructure in code, you can easily view the resources you've provisioned and ensure that only necessary resources are being used. Reducing waste and avoiding over-provisioning. Plan and review. Before applying changes, Terraform can show a plan of what will be changed, added, or destroyed, allowing teams to review and assess any cost impacts. 7. Security and compliance. Enforcement of standards. Using IAC allows teams to enforce security and compliance policies as part of the infrastructure configuration, for example. Ensuring encryption is enabled. Access controls are set up. Automated audits. With version-controlled infrastructure, it's easy to conduct audits and track who made what changes, helping to maintain security and compliance standards. 8. Infrastructure Lifecycle Management. State management. Terraform keeps track of the current state of the infrastructure, making it easier to manage complex dependencies and make incremental changes without manually updating resources. Easy updates. You can apply changes incrementally with Terraform Plan, ensuring only the necessary updates are made to your infrastructure. These benefits combine to make infrastructure management more efficient, reliable, and easier to maintain, especially as environments grow more complex. What are the core items of Terraform? The core items of Terraform are the fundamental components that make up the infrastructure as code, IAC, workflow. These components are essential for defining, managing, and deploying infrastructure in a consistent and automated manner. 1. Providers. 1. Definition. Providers are responsible for interacting with external APIs to manage the infrastructure. Each provider is specific to a cloud platform or service, for example, AWS, Azure, Google, Cloud, Kubernetes, etc. 4. Terraform Guide. Function. They define the resources you can manage, such as EC2 instances in AWS or virtual machines in Azure. For example, Provider AWS2. Resources. Definition. Resources represent individual infrastructure components that you want to manage with Terraform, such as virtual machines, networks, or storage buckets. Function. Resources are the building blocks of your infrastructure and are the actual items that are created, modified, or destroyed. For example, resource ES instance example 3. Variables ES instance example 3. Definition. Variables allow you to parameterize your Terraform configurations, making them reusable and dynamic by defining values that can be passed into your configuration. Function. They allow you to customize values like region, instance type, etc., without hard-coding them into the Terraform configuration. For example, variable instance, type 4. Outputs or. Definition. Outputs are used to expose important information about the infrastructure after a Terraform run, such as IP addresses or resource IDs. Function. They allow you to capture and display values for use in other processes, like showing the public IP of an EC2 instance. Example. Output instance. KIP 5. Modules 5. Terraform Guide. Definition. A module is a container for multiple Terraform resources that are used together. Modules can be reused across different configurations, allowing for code organization and sharing. Share function. Modules help in organizing complex Terraform configurations and in reusing code. You can use both local modules in your own codebase and external modules from the Terraform registry. For example, Module VPC 6. State definition. Terraform state is a representation of the current state of your infrastructure. Terraform uses it to map the real-world infrastructure to your configuration and to detect changes. Function. The state file keeps track of the resources Terraform manages and is critical for operations like Terraform plan and Terraform apply. It helps in determining what changes need to be made to the infrastructure. Example. The state is typically stored in a file called Terraform tf state, but it can also be stored remotely, for example, AWS 3, in a remote backend for better collaboration. 7. Data sources definition. Data sources allow you to query existing infrastructure outside of Terraform's management. This can be data from the cloud provider that you want to reference in your configuration. Function. They are used when you need to get information about existing resources, for example the ID of a subnet or a security group. Example, data Ozama latest 08. Backend definition. The backend in Terraform determines where the Terraform state is stored. It defines how and where the state file is managed, locally or remotely. Function. It helps with state management, enables collaboration, and provides features like state locking to prevent concurrent changes. Real origin. Terraform guide example. Dependencies 3 backend. Terraform 99. Provisioners chain definition. Provisioners allow you to execute scripts or commands on the resources after they are created or updated. They are typically used for bootstrapping instances or configuring infrastructure after it's been provisioned. Function. Provisioners are generally used to install software, configure services, or run initialization tasks on newly created resources. JAL example. Resource X instance example, conclusion. The core items of Terraform are the fundamental components that enable the creation, modification, and management of infrastructure. These include the providers to interact with APIs, resources representing infrastructure components, variables for parameterization, outputs for exposing useful information, modules for organizing and reusing code. D. State, to keep track of the infrastructure's real state. Data sources, to fetch information about existing resources. Backend, to store state remotely. Provisioners, for resource initialization. Terraform guide. The primary purpose of a Terraform workflow in a team setting is to. In a team environment, a Terraform workflow establishes a standardized approach for teams to collaboratively write, review, and apply infrastructure changes. It typically involves the following steps. 1. Write code. Developers and operators write Terraform configuration files to define the infrastructure. 2. Version control. These files are stored in a version control system, like Git, ensuring changes are tracked and versioned. 3. Plan. The Terraform plan command is used to preview changes before applying them, which helps teams assess the impact of changes. 4. Review. Changes are reviewed by team members through pull requests or code reviews, ensuring correctness, security, and alignment with best practices. 5. Apply. Once reviewed, the Terraform apply command is run to provision or update the infrastructure. State management. The state of the infrastructure is managed and updated in a shared backend, for example, Terraform Cloud. 3. Ensuring all team members work with the most up-to-date infrastructure. We need multiple provider instances in Terraform for several important reasons. 1. Manage multiple environments, for example, dev, staging, prod. Separate configurations. You might want to manage different environments, such as development, staging, and production, that require separate configurations, resources, or access controls. Using multiple provider instances, you can define different provider configurations for each environment to ensure isolation and proper resource management. Environment-specific variables. Each environment might use different credentials, regions, or resource configurations. Multiple provider instances allow you to handle these differences without affecting other environments. 2. Target resources in different regions, accounts, or endpoints. Region-specific resources. For cloud providers like AWS, Azure, or Google Cloud, resources are often created within specific regions. You may need to manage resources in multiple regions within the same provider, and using multiple provider instances allows you to do this seamlessly. Cross-account endpoint management. You can configure different provider instances to manage resources in different cloud accounts or across different endpoints, for example. Managing resources on premises in addition to the cloud. This flexibility is key for organizations that operate across multiple accounts or have hybrid cloud environments. 3. Managing multiple clouds. For example, AWS, Azure, Google Cloud. Multi-cloud architecture. In modern infrastructures, organizations often leverage more than one cloud provider, for example, using AWS for compute, Azure for networking, and Google Cloud for machine. 8a. Terraform guide learning. With multiple provider instances, Terraform allows you to manage resources across these different platforms within a single project. Consistency across providers. You can use a unified Terraform workflow to ensure that infrastructure is defined in code and deployed consistently across multiple clouds. 4. Isolation of resource configurations. Clear separation of responsibilities. If you're managing resources in different contexts, for example, one provider for core infrastructure and another for a specific service, using multiple provider instances helps maintain a clean separation of configurations. This can help avoid accidental resource conflicts or mismanagement. Granular control. Each provider instance can have its own set of configurations, such as authentication credentials, access keys, or region settings. This level of granularity makes it easier to control and manage your infrastructure. Example. To manage resources in both AWS and Azure, you might define two provider instances. Provider AWS provider, Azure where resource AWS instance. My instance resource Azure virtual. Machine my IE. Why? In this case, you have separate provider blocks for AWS and Azure, each managing its respective resources. 9. Terraform guide. Describe the lifecycle of a Terraform resource. The lifecycle of a Terraform resource describes how Terraform manages the creation, modification, and destruction of infrastructure resources over time. It consists of the following phases. 1. Configuration. You define the desired infrastructure in TF files using HCL, HashiCorp configuration language. Resource AWS instance, example 2. Initialization, Terraform init. Terraform initializes the working directory, downloads provider plugins, and prepares the environment. 3. Planning. Terraform plan. Terraform compares the current state, in the TF state file, to your configuration and shows an execution plan. It determines what to create, plus, update, destroy. 4. Apply. Terraform apply. Terraform applies the execution plan, creates new resources and modifies existing ones, destroys resources that no longer exist in your configuration. Changes are made via API calls to your cloud, SaaS providers. 5. State update. After applying, Terraform updates the state file, Terraform.tfa state, to reflect the real infrastructure. The state file is Terraform's single source of truth. 10. Terraform Guide 6. Lifecycle meta-arguments, optional control. You can influence the behavior of resources using lifecycle blocks. Resource AWS instance example. Prevent destroy. Stops accidental deletion date creator before destroy. Ensures safe replacement ignore changes. Prevents reapply on specific attribute changes. 7. Destroy. Terraform destroy. Terraform tears down all managed resources and updates the state file accordingly. Summary table phase description. Configuration. Write desired infrastructure code init. Initialize a directory and download providers. Plan show changes needed to match config apply. Make changes to real infrastructure state update. Record the new state of resources. Lifecycle options add fine-grained control. Prevent destroy etc. Destroy. Remove all managed infrastructure. Terraform state list. All the resources currently tracked in the Terraform state file. These are the resources Terraform is managing. 11. Terraform guide example. Terraform state list, output. AWS, instance, ducket AWS, is ducket, taunt unbucket. AWS, VPC, main. Y. The other options are incorrect. The other options are incorrect. 1. Terraform show displays the full state file content, including values, but not as a simple list. 3. Terraform validate only checks whether the syntax and configuration are valid. It doesn't list resources. A4. Terraform output shows the outputs defined in the configuration, not a list of resources. Here are a few scenarios where Terraform plan may pass, but Terraform apply can still fail. 1. Permissions issues each mal. Scenario. You have valid configurations, and Terraform plan shows no errors, but when you apply, Terraform tries to create or modify resources, and it encounters permission issues in your cloud provider, for example, AWS AM. Example. Terraform plan successfully shows what will be created. When you run Terraform apply, Terraform tries to create an EC2 instance, but the IAM role used by Terraform doesn't have sufficient permissions to create EC2 instances. Error during Terraform apply. Error. Access denied. User is not authorized to perform. ET2. Run instances 2. Provider configuration issues EAS. Scenario. You may have valid provider configurations, and Terraform plan may succeed. However, there could be an issue with provider authentication or other settings that only become evident when you attempt to apply the changes. Example. Terraform plan successfully generates a plan for resource creation. When you run Terraform apply, Terraform can't authenticate with the provider because your credentials have expired or are not set up properly. Error during Terraform apply. Error. Authentication failed. Invalid credentials 12. Terraform Guide 3. Resource dependencies not met. A might have defined resources with dependencies, but those dependencies aren't satisfied at the time of Terraform apply. Example. Terraform plan runs successfully because Terraform just checks the configuration and finds no issues. When you run Terraform apply, Terraform tries to create a resource that depends on another resource that hasn't been created yet due to an unmet dependency or missing configuration. Error during Terraform apply. Error. Resource AWS security group not found for. Out of sync infrastructure. Drift. Scenario. Infrastructure that was manually modified or deleted. Drift. But Terraform plan doesn't detect it. Or it doesn't show up in the state, causing Terraform apply to fail when it tries to reconcile. Example. Terraform plan runs and shows no changes, but manually deleting a resource. For example, an EC2 instance doesn't update the state. Terraform apply tries to modify or delete the resource, and AWS fails because the resource doesn't exist anymore. Error during Terraform apply. Error. Instance I went and etc x x not found. 5. Resource state mismatch for a scenario. There is a discrepancy between the local state file and the actual infrastructure due to state file corruption or manipulation. Example. Terraform plan runs and assumes the state is up to date. During Terraform apply, Terraform detects that the state file is out of sync with the actual infrastructure and fails to apply the changes. Error during Terraform apply. Error: state conflict detected. The state file is out of sync with real infrastructure. 6. Terraform resource update limitations (ULs). Scenario: certain resources might have limitations when it comes to updates. Terraform can plan updates, but the provider might prevent it. For example, you modify a resource that has restrictions on in-place updates, like changing the size of a managed disk in Azure. Terraform plan shows the change. Terraform guide. When you run Terraform apply, it fails because the resource can't be updated in place, and Terraform tries to recreate it. Error during Terraform apply. Error: cannot modify disk size of managed disk. It must be recreated. 7. Race conditions with resources. Scenario: if there are multiple teams or processes interacting with the same infrastructure, for example, creating resources in parallel, Terraform's plan might pass, but Terraform apply might fail due to a resource being modified or deleted by another process in the meantime. Example: Terraform plan shows that everything is ready. In the middle of applying, a resource like an S3 bucket is deleted manually or by another process, causing the apply step to fail. Error during Terraform apply. Error: bucket not found. The specified bucket does not exist. 8. Invalid resource modifications. Scenario: you modify a resource in a way that is technically valid in the configuration, but it violates constraints in the cloud provider or system that can only be detected during execution. Example: you change the instance type for an EC2 instance in your configuration. Terraform plan shows the plan change. During Terraform apply, AWS fails to stop the instance to apply the change due to a constraint, like the instance running critical workloads. Error during Terraform apply. Error: instance cannot be stopped. It is in use by a critical service. Summary of scenarios. 1. Permissions issues. Terraform has no issues planning, but lacks permissions to apply changes. 2. Provider configuration issues. Misconfigured provider settings. 3. Resource dependencies Dependencies are not in place. 4. Out of sync infrastructure. Manual changes cause discrepancies. State file, mint infrastructure are out of sync. 6. Resource update limitations. Certain updates can't be performed in place. 7. Race conditions. Resource modified, deleted by another process. 8. Invalid resource modifications. Changes violate cloud provider constraints. 14. Terraform guide. What are provisioners? How do you define provisioners? What are the types of provisioners in Terraform are used to execute scripts or commands on resources as part of the resource creation or modification process. They allow you to customize resources further after they are created, such as installing software, configuring systems, or running initialization tasks. Provisioners can be applied to any resource and are typically used to configure the environment once the resource itself is provisioned. How to define provisioners? Provisioners are defined within the resource block, using a provisioner argument followed by a specific provisioner type and configuration. Example: resource AEU is instance example. In this example, the remote exec provisioner is used to execute a series of commands on the newly created UGUS EXEC instance. Types of provisioners. 1. Local exec. Executes commands on the machine running Terraform, the local machine, during the resource creation or modification. Example: provisioner local exec. 2. Remote exec. Executes commands on a remote machine after the resource is created, typically via SSH or Win for Windows. This is commonly used to configure instances post-deployment. Example. 15. Terraform Guide Provisioner Remote XXV3. File copies files from the local machine to the remote machine. It is useful when you need to upload configuration files, scripts, or other resources to a remote instance. Example. Provisioner file when to use provisioners. Provisioners should be used cautiously, because they can create dependencies on the order of resource creation. They should be reserved for situations where resource creation alone doesn't fully configure the system. Additionally, it's often better to use configuration management tools. For example, Ansible, Puppet, Chef, for long-term infrastructure management, instead of relying heavily on provisioners. What is taint? When are resources marked tainted? In Terraform, tainting refers to the process of marking a resource as needing to be recreated, even if it hasn't changed according to the Terraform plan. When a resource is marked as tainted, Terraform will destroy and recreate that resource during the next apply. What is taint? A tainted resource is one that has been flagged for destruction and recreation. Tainting a resource in Terraform means that Terraform will destroy the existing resource and recreate it on the next apply, even if there were no changes to its configuration. This is useful in cases where the resource has been corrupted, has become inconsistent, or needs to be re-provisioned for other reasons, even though the configuration has not changed. 16. Terraform Guide when a resource is marked tainted. Resources can be marked tainted in a few ways. 1. Manual tainting. You can manually taint a resource by using the Terraform taint command. This explicitly marks the resource for destruction and recreation on the next Terraform apply. Example. Terraform taint AWS instance.example. In this case, the AWS instance.example resource will be marked as tainted, and it will be destroyed and recreated the next time Terraform apply is run. 2. Implicit tainting. State drift. Sometimes, resources are implicitly tainted by Terraform if it detects that the actual state of the resource has drifted from the desired configuration. This can happen due to manual changes made to the resource outside of Terraform, or because of infrastructure issues that make the resource unhealthy. Terraform will notice that the resource no longer matches the desired state and will mark it as tainted so it can be replaced. 3. Failed resource creation or updates. If a resource creation or update fails during a Terraform apply operation, Terraform may mark the resource as tainted. This often happens when a resource is created but there was an issue with it. For example, a provisioning script failed or an API returned an error, and Terraform knows that the resource cannot be used as is. 4. External factors. Resource corruption. If external systems or manual actions, such as an operator manually deleting or modifying the resource, cause the resource to be in a bad state, Terraform can detect this during the next plan, or apply and mark it as tainted. How to manage tainted resources. 1. Recreating a tainted resource. Once a resource is tainted, Terraform will recreate it during the next apply. You can check the taint status by running Terraform show. It will indicate which resources are tainted. To apply the changes and recreate the resource, you simply run Terraform apply. 2. Untainting a resource. If you decide that a resource shouldn't be tainted anymore, you can untarget it using the Terraform untaint command. 17. Terraform Guide, Terraform Untaint AWS, Example 3. Use in CI/CD pipelines. Tainting can be useful in CI/CD pipelines when you want to ensure resources are recreated each time to maintain consistency. For example, to get fresh environments or to resolve issues that might arise from stale resources. Why is tainting useful? G. Correcting unhealthy resources. If a resource is in a bad state, for example, misconfigured, corrupted, or non-functional, tainting forces Terraform to destroy and recreate it to ensure that the infrastructure is in the desired state. 1 and all. Forced reprovisioning. Tainting can be used when you need to force a resource to be reprovisioned. such as when changes need to be applied that Terraform does not automatically detect, for example, manual changes. What is a workspace? When and how to use it? A workspace in Terraform is an isolated environment within a Terraform configuration that allows you to manage multiple versions of infrastructure using the same codebase. Workspaces help you manage different stages of infrastructure, for example, development, staging, production, without needing to duplicate your configuration files. What is a workspace? A workspace is essentially a container for Terraform state files. By default, Terraform uses a default workspace, but you can create multiple workspaces to isolate state files for different environments. Each workspace has its own state and set of variables, making it easier to manage different environments or configurations. Terraform workspaces allow you to manage different environments, for example, dev, staging, production, with the same Terraform code, or keep state isolated per environment, preventing interference between environments. Use the same Terraform configuration for multiple environments by using workspace-specific variables and state. When to use workspaces? You might want to use workspaces in the following scenarios. Multi-environment deployments. When you want to use the same Terraform code to manage different environments, for example, separate resources for development, staging, and production. Testing multiple versions of infrastructure. When you need to test changes to infrastructure in a temporary isolated environment without affecting the main infrastructure. 18. Terraform Guide. Managing different configurations for a single project. When the configuration changes based on the workspace, for example, using different resources or settings for different environments. How to use workspaces. 1. Creating a new workspace. You can create a new workspace using the Terraform Workspace New command. Example: Terraform Workspace New Dev. This will create a new workspace named Dev. 2. Switching between workspaces to switch to an existing workspace. Use the Terraform Workspace Select command. Example: Terraform Workspace Select DV. This command switches to the dev workspace. Terraform will now manage infrastructure for the dev environment. 3. Listing workspaces. To view all available workspaces, use the Terraform Workspace List command. Example: Terraform Workspace List. This will show all the workspaces that exist in the current project. 4. Workspace-specific variables. You can define different variables for each workspace. You can use Terraform Workspace to reference the current workspace inside your Terraform configurations. Example: Variable instance. Type: resource. Example 19. Terraform Guide. In this example, the Terraform Workspace variable dynamically adds the workspace name to the name tag, making it clear which environment the resource belongs to. 5. State isolation. Each workspace has its own state file. When you switch workspaces, Terraform uses a different state file, ensuring that your infrastructure for different environments does not interfere with one another. You can check the current workspace by running Terraform Workspace Show. This will display the current workspace, such as dev, staging, or production. 6. Deleting a workspace. If you no longer need a workspace, you can delete it using the Terraform Workspace Delete command. Defend. Pado. Note that deleting a workspace will not delete the actual resources in your cloud provider, just the state associated with that workspace. Example: Terraform Workspace Delete Dev. Example use case. Let's say you are working on a project that requires separate environments for development, staging, and production. You can use workspaces to manage these environments. 1. Create a new workspace for each environment. Terraform Workspace, New, Dev. Terraform Workspace, New Staging, Terraform Workspace, New Production. 2. Use Terraform Workspace in your configuration to set different variables or configurations for each environment. For example, different instance types in each environment. 3. Switch between workspaces based on the environment you are working on. Terraform Workspace, select Dev Terraform, apply. 4. Once you're ready to deploy to production, switch to the production workspace. Terraform Workspace, select Production Terraform, apply. 21. Terraform Guide Best Practices. Use workspaces to isolate different environments, for example, development, staging, production, while using the same Terraform codebase. Avoid using workspaces for multi-region or multi-tenant configurations that have complex dependencies across different states. Use workspaces with caution in CI/CD pipelines, as managing state correctly in these environments is critical to avoid accidental modifications. If different teams are working on the same configuration, how do you make files to have consistent formatting? To ensure consistent formatting of Terraform configuration files when different teams are working on the same codebase, you should use Terraform FMT Terraform Format. This command automatically formats your TF and TFRs files according to the standard Terraform style conventions. Here's how to implement it in a team setting. 1. Use Terraform FMT locally. Developers should run Terraform FMT before committing code. JAL example, Terraform FMT recursive. This formats all Terraform files in the current directory and subdirectories. 2. Enforce with pre-commit hook. Use a git pre-commit hook to auto-format files before they're committed. Hash git hooks pre-commit Terraform FMT recursive. 3. Integrate into 101 pipeline 1. Add a formatting check in your 101. For example, GitHub Actions, GitLab C Jenkins, to ensure PRs have properly formatted code. Terraform FMT check recursive. This fails the build if any file is incorrectly formatted. 21. Terraform Guide 4. Use editor plugins. Most IDEs, for example, VS Code IntelliJ, have Terraform plugins extensions that format code on save using Terraform FMT. Summary. Using Terraform FMT ensures clean, consistent formatting, reduces merge conflicts, and improves readability and collaboration across teams. Explain difference between Terraform FMT and Terraform Validate with examples. Great question. Both Terraform FMT and Terraform Validate are essential Terraform commands, but they serve very different purposes. Terraform FMT, formatting. Purpose. Automatically formats your Terraform configuration files to follow the standard style guide. Dual use case. Keeps your code clean and consistently styled. Does not check for correctness, only formatting. Example. Before running Terraform FMT, resource AWS instance example run. Terraform FM2. After running Terraform FMT, resource AWS instance example. It fixes spacing, alignment, and block formatting automatically. 22.2. Terraform Guide. Terraform Validate. Syntax and configuration validation. Purpose. Validates that the Terraform files are syntactically valid and internally consistent. Checks for errors in syntax, required arguments, or logical issues. All does not interact with any real infrastructure or providers. Example. Invalid configuration. Resource auth instance example. Run. Terraform Validate output. Error. Missing required argument on main TF line 1 in resource AWS instance example. 1. Resource exe instance example. Terraform Guide. If Terraform crashes during execution, which of the following steps can you take to debug the issue and gather more information? If Terraform crashes during execution, there are several steps you can take to debug the issue and gather more information to diagnose the cause of the crash. Here are the common steps. 1. Check Terraform logs, TFE-log. Terraform provides detailed logging capabilities through the TFE-log environment variable. This can give you more insight into what Terraform was doing at the time of the crash. Do set tflog to debug or trace To get detailed debug level or trace level logs, export TF logs debug. Or, for even more detailed output, export TF log trace. Once set, Terraform will output detailed logs to the console, which can help identify the exact point of failure or provide more context about the issue. If you want to store the log output in a file, use export TFI log path, terraform.log. This is a powerful tool for investigating crashes and troubleshooting unexpected behavior in Terraform. 2. Review the crash output after a crash. Terraform usually prints an error message or stack trace to the console. This is often the first place to look for clues about what went wrong. Carefully review the error message and stack trace to determine if there's any specific resource or operation that is causing the crash. 3. Use Terraform Plan for validation. If you're unsure about what changes Terraform is trying to make, you can run Terraform Plan to preview the changes before actually applying them. This can help you catch any obvious issues before a crash occurs during execution. Terraform Plan. This command shows what Terraform intends to do, which might give insight into what causes the crash during the apply. 4. Run Terraform with debug flag 24. Terraform Guide. Running Terraform with the debug flag forces Terraform to output debug level information, which can be helpful in understanding the crash. Terraform Apply Debug. 5. Check Terraform version and providers. Ensure that you're using a stable version of Terraform, and check for any issues related to your version by visiting the Terraform GitHub repository or the Terraform release notes. Similarly, check that all the provider plugins you're using are up to date. Sometimes crashes are due to bugs in older versions of the provider plugins. To check your current Terraform version, Terraform version 6. Examine the state file. Corrupted or inconsistent state files can sometimes lead to crashes during execution. If you suspect the state file is the issue, try running Terraform state list. This will show the resources in your state file and allow you to verify that it hasn't become corrupted. If you suspect corruption, you can try to manually inspect or repair the state file. For example, using Terraform state commands. 7. Increase system resources. Terraform can crash if it runs out of memory or other system resources during execution, especially when managing large infrastructures. Check your system's resource usage, CPU, RAM, disk, to ensure that it has enough resources to handle the workload. You can also try running Terraform on a machine with more memory or CPU resources if possible. 8. Update dependencies. If the crash happens during a specific provider's resource management, ensure that all providers are updated. Run the following command to upgrade all provider versions to the latest compatible version. Terraform init, upgrade 9. Isolate the problem. If you're unable to identify the crash from logs or output, try isolating the issue. 25. Terraform Guide. Comment out sections of the configuration, or remove some resources temporarily to narrow down the specific resource causing the crash. Run smaller configurations to verify if a particular resource or module is causing the crash. 10. Check for known issues. After reviewing the logs, check if the error matches any known issues by searching for it in the Terraform GitHub issues or related provider repositories. 11. Contact HashiCorp support. If you're able to resolve the issue, and you have a Terraform Enterprise subscription or support plan, you can contact HashiCorp support for further assistance. Summary of steps. 1. Set TF log debug or TF log trace for detailed logs. 2. Review the crash output for error messages or stack traces. 3. Run Terraform plan to check the intended changes before applying. 4. Use the debug flag to get more detailed information during execution. 5. Ensure you're using the latest Terraform and provider versions. 6. Check the state file for inconsistencies. 7. Monitor system resources to avoid running out of memory or CPU. 8. Isolate the problem by commenting out parts of the configuration. 9. Search for known issues related to the error. 10. Contact HashiCorp support if needed. What is module? Where do you find and explore Terraform modules? How do you make sure that module have stability and compatibility? Explain with example. In Terraform, a module is a container for multiple resources that are used together. A module allows you to group and organize resources logically, and reuse them across different configurations. Modules help in abstracting away complex infrastructure logic into reusable units of work. They can be local to your project or sourced from public or private module repositories. Key benefits of using modules. Reusability. Modules allow you to create reusable infrastructure components that can be easily applied in different configurations. Maintainability. You can organize your Terraform configuration into modular units, making it easier to manage, maintain, and update. Abstraction. Modules can abstract away complex infrastructure setups, making it easier to work with simple interface inputs. 26. Terraform Guide. Scalability. By using modules, you can scale your infrastructure management by reusing predefined modules in different parts of your infrastructure. Where to find and explore Terraform modules. Terraform modules can be sourced from various locations. 1. Terraform Registry. The Terraform Registry. Terraform is the primary place to discover, explore, and share modules. It contains a large collection of modules for different cloud providers and use cases. Example module search. Terraform modules. 2. GitHub. Many Terraform modules are hosted on GitHub repositories. You can find them by searching for specific keywords or by browsing through popular Terraform module repositories. 3. Private repositories. You can create your own private module repositories for your organization's infrastructure needs. 4. Community contributions. Many organizations and developers share modules through blogs, forums, or dedicated repositories like GitHub. It's often useful to review community modules to see if they fit your needs. Example of using a module from Terraform Registry. Here is an example of how you can use a module to deploy an AWS EC2 instance. This module can be found on the Terraform Registry. Module EC2 instance. Source. The source points to the module's location. In this case, it's a publicly available module from the Terraform AWS modules collection on the Terraform Registry. The module will automatically create an EC2 instance using the provided parameters like MI, instance type, and name. How to make sure a module has stability and compatibility. To ensure that the module you are using is stable and compatible, you can take the following steps. 27. Terraform Guide 1. Check module version. Many modules in the Terraform registry support versioning. By specifying a version in the source parameter, you ensure that you are using a stable and compatible version of the module. Example. Module EC2 instance. The version constraint, in3, ensures that Terraform uses a stable version from the 3.x series, ensuring compatibility with your setup. If you do not specify a version, Terraform will fetch the latest version, which may introduce breaking changes. 2. Review module documentation. Always check the module documentation on the Terraform registry or the module's repository. Well-documented modules will provide details about the inputs and outputs, variables and return values, examples of usage, compatibility with different versions of Terraform and the providers, known issues and limitations, required dependencies and the module's supported features. This helps to ensure the module meets your needs and works as expected in your environment. 3. Check for active maintenance. Ensure the module is actively maintained by checking the commit history on GitHub. If using a module from there, look for recent commits and releases to verify ongoing support. If the module has not been updated in a long time, it could be deprecated or incompatible with newer Terraform versions. Example of checking maintenance activity. GitHub repositories commit history. L module release tags or changelog. 4. Read community feedback. Review community feedback, issues, and pull requests. In the Terraform registry, you can often find user reviews and issues posted by others who have used the module. This can help identify any known bugs or incompatibility issues. GitHub repositories often have an issues section where users report problems, and you can gauge if these issues are being actively addressed. 28. Terraform Guide 5. Testing and validation. B. Before using a module in production, always test it in a staging or development environment. Validate the configuration by running Terraform plan to check the changes that the module will apply. You can also review the resource outputs and their behavior in a test environment to ensure the module is working as expected. 6. Module compatibility with Terraform version. Ensure that the module is compatible with the version of Terraform you are using. Some modules may require specific Terraform versions due to changes in the Terraform language or provider APIs. Check the module's documentation or changelog for any version restrictions. 7. Check input variables and defaults. Look for any input variables and their default values. For example, the instance type variable in the EC2 module might have a default value, but you can override it to better fit your infrastructure needs. Example: variable instance type. By reviewing and adjusting variables, you can make the module work in a variety of contexts, improving its stability for your environment. Example: verifying stability and compatibility. If you are using a module to provision an AWS RDS instance, you can ensure its stability and compatibility by 1. Specifying the version, module RDS. 2. Reviewing the module's documentation for supported AWS regions and Terraform versions. 3. Checking GitHub issues to see if others have faced compatibility issues or bugs. 4. Testing the module in a staging environment before deploying it in production. 29. Terraform Guide Conclusion. Terraform modules help you reuse and share infrastructure code. To ensure that the modules you use are stable and compatible, always specify versions. Review module documentation carefully. Check the module's maintenance status and community feedback. Test the module in a controlled environment. Test the module in a controlled environment. Validate compatibility with your Terraform version. What's variable? Types and examples. Explain precedence. A variable in Terraform is a way to input data into your configuration. It enables you to customize the infrastructure deployment by passing in different values when applying the configuration. Types of variables in Terraform. 1. Input variables. These are variables defined in Terraform configurations that allow you to pass dynamic values into your modules or resources. Example: variable region. In this example, the region variable is defined to allow dynamic configuration of the region for AWS resources. 2. Output variables. These variables capture values from your Terraform resources and output them after the plan is applied. This is useful for exporting data like IP addresses or resource IDs. Example: output instance IP. The instance IP output variable stores the public IP address of the AWS EC2 instance. Terraform Guide 3. Local values. Local values are named expressions that can be used to simplify your Terraform code. They're similar to variables but are used within the configuration to store intermediate results. Example: locals. The instance type local value simplifies referencing the EC2 instance type in your configuration. Variable types in Terraform. When defining input variables, you can specify a type to control the kind of data that can be passed in. 1. String, a variable that holds a text value. Variable environment. A variable that holds numeric values. Variable instance. Count 3. Bool, a variable that holds a boolean, true or false, value. Variable enabled logging. 4. List, a variable that holds an ordered collection of values, where each value is of the same type. Variable availability zones. 5. Map a variable that holds a collection of key value pairs, where the key is a string, and the value can be any data type. Variable instance. Tags. Terraform guide type map, string, default objects. Object a variable that holds a complex structure with specific attributes. Variable server, default OWA. Example of defining and using variables in Terraform. Here's an example of defining input variables, assigning them values, and using them within a resource configuration. Variable region, variable instance type, resource AUS instance example. Precedence of variables in Terraform. Terraform variables follow a precedence order when values are assigned. Here's the order in which Terraform looks for values for a variable. 32. Terraform Guide 1. Environment variables. You can set variables using environment variables, and these will override values set in tvars files or default values in the configuration. Environment variables are named as tfvar. Example, tf var region gus west 22. 151. Arguments when running Terraform apply. You can pass variables via the command line using the var flag. These override environment variables. Ow. Day. 1 so. TFVAR's files and defaults in the configuration. Example. Terraform apply. var region gus west. 23. TFVAR's files. If you have a file named terraform.tfvars, or any tfvars file, Terraform will automatically load the values from that file. These values will override the default values in the configuration, but are overridden by the environment variables and 151 arguments. 4. Default values. The default value of the variable is used if no value is provided via CLI, TIA, vars files, or environment variables. Example of variable precedence. Variable region. #terraform.tfvars region to AUS west. 2. If you run Terraform apply without passing any variables, it will use us west 2 from the tfvars file instead of the default us east 1. But if you pass the variable through the command line, Terraform apply var region gus west 3, it will use us west 3 instead of us west 2 or the default us east 133. Terraform guide. What is the purpose of using a Terraform remote backend? A Terraform remote backend is used to manage the state files of a Terraform project in a centralized location. The state file contains important information about the infrastructure managed by Terraform, and using a remote backend allows teams to share and collaborate on the same infrastructure without conflicts. Remote backends provide several benefits. Centralized storage. The state files are stored remotely, for example in AWS 3, Azure, blob storage, etc., ensuring all team members are working with the same version of the state file. Collaboration. Multiple users can work on the same infrastructure concurrently without the risk of overwriting each other's changes. State locking. Some remote backends, like S3 with Dynamod or Azure blob storage, support state locking, which prevents concurrent modifications to the state file. Security. State files may contain sensitive information, and remote backends can provide encryption and access control to protect this data. Why the other options are incorrect. 1. To store Terraform configuration files in a central location. Terraform configuration files, TF files, are typically version controlled in a source code repository like Git, not stored in a remote backend. 2. To execute Terraform commands remotely without local setup. Terraform backends are not designed to execute commands remotely. They only manage state storage. Terraform commands are still executed locally on your machine or CI/CD system. 3. To store the Terraform provider plugins. Provider plugins are stored locally or downloaded from the Terraform registry, not within the remote backend. The backend stores the state of the infrastructure. So, The purpose of a remote backend is primarily to centralize the storage and management of Terraform state files. The purpose of using a Terraform remote backend is to store and manage Terraform state files in a centralized, secure, and accessible location. This allows for better collaboration, state management, and ensures that teams can safely and efficiently work together on shared infrastructure. Key purposes of a remote backend. 1. Centralized state storage. Storing Terraform state remotely helps ensure that the state of your infrastructure is consistently shared and updated across teams or environments. The state file holds crucial information about the infrastructure, and using a remote backend avoids local state files that can be out of sync or lost. 2. Collaboration and team support. With remote state, multiple team members can work on the same infrastructure concurrently without interfering with each other's work. The backend ensures that everyone is working with the most recent version of the state file, enabling collaboration. 3. State locking. Many remote backends, like Gig.us, SRI with Dynamob, or Azure Blob Storage, support state file 34. Terraform guide locking, which prevents concurrent updates to the state file, avoiding potential conflicts or corruption of the state. 4. Security. Remote backends often offer additional security features, such as encrypted storage and fine-grained access control, ensuring that sensitive data in the state file, like resource credentials, is protected. 5. Scalability. Using a remote backend is essential for large, complex Terraform deployments that need to scale across multiple teams, regions, or environments, as it centralizes and simplifies state management. 6. Integration with version control and CI/CD. With remote backends, it's easier to integrate Terraform with CI/CD pipelines and version control systems, ensuring that infrastructure changes are tracked and versioned. Common remote backend solutions. Amazon S3 with DynamoB for locking. Used to store state files in S3 and use DynamoB for state locking. Azure Blob Storage, a scalable solution for storing Terraform state on Azure. HashiCorp Console, a distributed, highly available key-value store that can be used for state storage and locking. Google Cloud Storage, GCS, a backend that stores state in GCS buckets. How can you import existing infrastructure into Terraform? In which scenario you need to use import? What are the limitations? Please explain with an example. You can use the Terraform import command to bring existing infrastructure under Terraform management. This command allows you to take resources that were created outside of Terraform, manually or by other means, and import them into the Terraform state so you can manage them going forward. The general syntax for the Terraform import command is Terraform import options. Nomed, where resource type is the type of resource, for example, Gig.us instance. All resource name is the name you want to give the resource in your Terraform configuration. Resource ID is the ID of the resource in the cloud provider, for example, Azure's EQ instance ID or Azure resource ID. Scenario for using Terraform import. You would use Terraform import in the following scenarios. 35. Terraform Guide 1. Managing pre-existing resources. When you have infrastructure that was created manually, through scripts, or by another team, and you want to bring it under Terraform management without recreating it. 2. Migrating from another tool. When migrating an existing infrastructure managed by another tool, like CloudFormation, or manually using the console, to Terraform. You can use Terraform import to bring those resources under Terraform control. 3. Working with hybrid environments. In a hybrid environment, you might want to combine resources that Terraform manages with those that were created manually or by other tools. 4. Refactoring infrastructure. If you've made changes manually in your cloud provider's console and want to keep Terraform in sync without recreating resources. Example of Terraform import. Let's assume you have an C2 instance in AWS, and you want to bring it under Terraform management. 1. Find the EC2 instance ID. In AWS, you can get the EC2 instance ID from the console, CLI, or API. Let's say the instance ID is I0abc 234.55678. 2. Import the EC2 instance. Use the Terraform import command to import the resource into Terraform. Terraform import AWS instance. Deg example I0abc 1234. 5678.3. Create the resource block. After importing, you need to manually create the corresponding resource block in your Terraform configuration file. For example, main.tf. Resource aux instance example. Once the import is successful, Terraform will have the instance in its state file, and the resource will be managed under Terraform. 4. Run Terraform plan. After importing, run Terraform plan to verify that Terraform recognizes the state of the resource and checks for any differences between the configuration and actual infrastructure. Terraform plan. 36. Terraform guide limitations of Terraform import. While Terraform import is powerful, there are a few limitations. 1. Does not create configuration files automatically. The Terraform import command only adds the resource to the state file. It does not generate Terraform configuration files. You must manually write the configuration block for the imported resource. 2. State-only operation. Importing a resource only affects the state file. It does not change the actual infrastructure or configuration. This means that Terraform does not automatically update your TF files to reflect the current resources settings. 3. Complex resources may need manual configuration. For some complex resources you may need to figure out the correct configuration settings manually. For example, an EC2 instance could have tags, security groups, or additional properties that are not automatically added during the import. 4. No import of dependencies. If the imported resource has dependencies, for example, security groups, roles, you must manually import those dependencies and configure them in your TF files. Terraform will not automatically detect these associated resources. 5. Cannot import all resource types. Not all resource types are supported by Terraform import. The resource must be supported by the Terraform provider, and some less common or custom resources may not be importable. 6. No historical changes in state. When you import an existing resource, Terraform does not have the history of changes made to that resource. You will not be able to track changes that occurred before the import, and you may miss insights into previous configurations unless you manually capture them. 7. Requires correct resource ID. You need to know the correct identifier for the resource you're importing. Without this, you won't be able to successfully import the resource. The ID format varies between providers. Example of limitations. Let's say you're importing an EC2 instance, but the instance has a custom security group attached that you didn't define. You'll need to import that security group separately and ensure that it's linked in your configuration. 1. Import the security group. Terraform import aux security group example SG 0 opsidon 234 55678. 2. Manually add security group to configuration. After importing the security group, you'll need to manually associate it with your EC2 instance in the configuration file. 37. Terraform Guide Conclusion. The Terraform import command allows you to bring existing infrastructure into Terraform's management, making it easier to manage and automate the configuration of pre-existing resources. However, you must manually write the corresponding Terraform configuration files. and be aware of its limitations, such as the inability to automatically import resource dependencies or generate configuration from existing infrastructure. Give few examples of lifecycle rules in Terraform. In Terraform, lifecycle rules are used to customize the behavior of resources when performing actions like creation, update, or destruction. These rules allow you to control how Terraform interacts with resources during these lifecycle events. Here are a few common examples of lifecycle rules in Terraform. 1. Create before destroy. Purpose. Ensures that a resource is created before the existing one is destroyed during updates. Use case. This is useful when you need to avoid downtime, or when a resource must exist before its replacement can be destroyed. For example, load balancers, databases. Resource security group example. Other security group properties. Aliens po id Dependencies alzechernli no. Dundai. Explanation. This rule ensures that the security group will be created first, and only once the new one is successfully created, the old one will be destroyed. To prevent destroy, prevent destroy. Purpose. Prevents the resource from being destroyed, even when a Terraform destroy or Terraform apply is executed. Use case. This is useful for critical resources where you do not want them to be deleted accidentally, such as production databases or stateful applications. Resource X instance example. Terraform guide lifecycle. Other instance properties. Explanation. The prevent destroy UI true setting ensures that the resource can't be destroyed, and an error will occur if you attempt to destroy the resource. 3. Ignore changes. Purpose. Tells Terraform to ignore specific changes to resource attributes during an update, effectively preventing Terraform from attempting to modify those attributes. Use case. This is useful when you have resources that are externally managed or updated, and you don't want Terraform to track changes to those attributes. For example, manual changes to tags or instance metadata. Resource AWS instance. Example, lifecycle. Explanation. In this example, Terraform will not attempt to change the name tag of the instance, even if the tag is modified outside of Terraform. 4. Replace triggered by purpose. This rule causes a resource to be replaced when a change to another resource or data source occurs, even if the change does not directly impact the resource. Use case. This is useful when a change in one resource triggers the need to replace another resource, even if the two are not directly related in Terraform's normal dependency graph. Resource AWS security group example. Terraform guide lifecycle. Explanation. In this example, if any changes occur to the tags of AWS security group example, Terraform will replace the security group, even if the change is unrelated to the resource's configuration. 5. Destroy before create purpose. Ensures that a resource is destroyed before a new one is created when making changes. Use case. This rule can be useful when you need to destroy a resource first before creating a new one, like when upgrading a resource that cannot be reused, or if it requires a downtime window. Resource AWS instance example. Other instance properties EU. Explanation. In this case, Terraform will destroy the instance first before creating the new instance, which could be useful for certain types of infrastructure changes. 6. Ignore changes for multiple attributes purpose. You can use ignore changes to ignore multiple attributes at once, preventing Terraform from making changes to them during an update. Use case. This is useful when you want to prevent updates to multiple properties that may be modified manually or managed externally. Resource A's instance example lifecycle. Terraform guide instance. Type hash. Ignore changes to instance type .t. Explanation. Terraform will ignore changes to the AMI and instance type properties, meaning that manual updates to these fields outside of Terraform won't trigger changes to the instance. Summary of lifecycle rules in Terraform. K created before. Ensures a resource is created before the previous one is destroyed, avoiding downtime. Prevent destroy. Prevents a resource from being destroyed. Useful for critical infrastructure. Ignore changes. Ignores specific changes to resource attributes during updates. Useful for externally managed attributes. Replace triggered B. Forces a resource to be replaced when changes to other resources or data sources occur. Destroy before creata. Destroys the resource before creating a new one. Useful for cases where recreating a resource is required. What interpolation in Terraform? Where to use? Interpolation in Terraform refers to the process of embedding dynamic expressions or values inside your Terraform configuration files. It allows you to reference variables, attributes, and data from other resources and pass them as input to other resources or configuration blocks. Interpolation is typically done using dollar syntax, where you can insert expressions that will be evaluated and replaced by actual values during the execution of Terraform plan or Terraform apply. Where to use interpolation in Terraform? Interpolation is used in various places within Terraform configurations such as 1. Variables. Referencing input variables inside the configuration. 2. Resource attributes. Using values from one resource to configure another. 3. Data sources. Accessing dynamic values from external sources. Lake. 4. Output values. Defining outputs that dynamically reference resource attributes. Examples of interpolation in Terraform 1. Using variables in configuration. You can use interpolation to reference variables within a resource or other parts of your Terraform configuration. 41. Terraform Guide Variable Instance. Type resource in WS. Instance example hash interpolating the value of instance. Type variable. Explanation. Here, the dollar interpolation is used to reference the instance type variable in the AWS instance resource. 2. Referencing resource attributes. Interpolation allows you to use attributes from one resource in another resource. This is particularly useful when you need to configure one resource based on the attributes of another. Resource AWS security group example. Resource instance example. A hash interpolating security group name. Explanation. The security group's attribute of the AWS instance resource is using interpolation to reference the name of the AWS security group. Example, resource. 3. Using outputs and expressions. You can also use interpolation in outputs to reference attributes or variables and output their values. Output instance. Hid hash interpolating the instance, IDD. Explanation. The value of the instance, id output is interpolating the ID attribute of the AWS instance X example resource. 4. String manipulation with interpolation. You can use interpolation to perform string manipulation in Terraform, like concatenating strings or combining values. 42. Terraform Guide Output Instance. Name hash. Concatenating a string with instance IDE explanation. The output instance name concatenates the string example with the ID of the EC2 instance, producing a dynamic name based on the instance. 5. Using expressions for conditional logic. Terraform allows for more complex expressions within interpolations. You can use conditions and functions to dynamically determine values. Resource AWS instance example, hash conditional interpolation. Explanation. This example uses a ternary operator for conditional interpolation. If var instance type is T2 micro, the instance type will be T2 small. Otherwise, it will be T2 medium. When to use interpolation in Terraform? You should use interpolation when 1. Referencing dynamic values. When you need to inject variables, resource attributes, or data into resource definitions. 2. Creating dynamic resources. When the configuration depends on other resources or variables, and you want to automate the creation of resources dynamically. 3. Combining values. When you need to combine different strings, variables, or values together to form a dynamic configuration. 4. Conditional logic. When you need to apply logic that decides which values or resources to use based on input conditions. 5. Outputting dynamic data. When creating outputs that represent the results of your infrastructure, such as resource IDs or URLs. Terraform 0.12 Plus and interpolation. Starting with Terraform 0.12 and beyond, interpolation is optional in many cases. Terraform automatically handles most situations without needing explicit interpolation. For instance, hash pre-Terraform 0.17. Interpolation was required. Output instance, nam hash, in Terraform 0.12 Plus. Interpolation can be omitted. Output instance, name. Terraform guide value, AWS instanced example, .id hash. Direct reference without interpolation. B. Conclusion. Interpolation in Terraform allows you to create dynamic configurations by referencing variables, resource attributes, or data sources. It is used for injecting variables into resource definitions, creating relationships between resources, generating dynamic output values, while performing string manipulations and conditional logic. Since Terraform 0.12 Plus, interpolation has become more intuitive, and in many cases, you don't need to use the $ syntax for simple references. But it's still essential to understand how and where to use it to make your configurations dynamic and flexible. How can you leverage Terraform's count and for each features for resource iteration? Terraform's count and for each are meta-arguments that allow you to create multiple instances of a resource, module, or block in a clean, efficient, and scalable way. These features are useful when you need to dynamically create resources based on input data like lists or maps. 1. Count. Basic iteration with index use case. Use count when you want to repeat the same resource multiple times, usually based on a list or number. Example. Creating multiple EC2 instances variable instance. Count resource AWS instance web, WAD, count 44. Terraform guide explanation. Creates 3 EC2 instances. All $ gives the current loop index 0, 1, 2, 2, 4 each. Iteration over maps or sets use case. Use for each when you want to create one resource per item in a map or set, and you want to access each key value clearly. Example. Creating multiple S3 buckets from a list variable bucket names, resource bucket buckets explanation. Each bucket will be created with the name from the list. Each key gives a current bucket name, like dev bucket. Example with for each using a map variable bucket config war as source. ABLIS 3 buckets, 45. Terraform guide explanation. Each key value pair becomes a resource. All each key dev. Prod each value add dev bucket. 123 etc. Count versus for each when to use. Feature use when you have. Key access style supports maps, index info, count a number or list count index Yes, for each a map or set of strings, each key each. Value. Case no. But you get keys. Real world use cases. Count. Create a number of subnets, EC2 instances, or IAM users. Authoric. Create resources based on unique names, for example, tagging policies, 3 buckets with meaningful names. Notes, you can't use both count and for each in the same resource. For dynamic resource creation where names keys matter, prefer for each. When using for each, your keys must be unique. You want to create security groups for dev, test, and prod environments. Using count input, variable environments Terraform code, resource AWS security group, count example description security group for $VPC, DPC. 1, 2, 3, 4, 5, 6, 46. Terraform guide tags HG points uses a list. You must access values using count.index. Way less readable when accessing attributes in complex structures. Using for each input. Variable and vaymap, YNE, VN. Terraform code. Resource AWS security group for each. Example description TOGI. Security group for $VPCED. Each value. Tags OG AG P points. Uses a map. Easier to read and manage key value structures. While each key is the environment, each value is the VPC ID. Summary table feature input type key access example use case 47. Terraform guide feature input type key access example. Use case count list, number count.index. Same resource repeated n times, for example, EAT2. For each map, set each key value named resources. For example, S3 buckets, SGS. How can you handle resource failures, retries in Terraform? In Terraform, handling resource failures and retries is crucial for maintaining a reliable and idempotent infrastructure as code workflow. Terraform doesn't natively offer granular retry policies like a programming language, but it provides several mechanisms to deal with transient failures and ensure resources are created reliably. 1. Terraform built-in retry mechanism. Terraform automatically retries failed operations like create, update, or delete for many providers, especially AWS, Azure, GCP. When the failure is transient, for example, throttling, rate limits, API timeouts, you don't have to write retries for most transient cloud issues. Terraform already does that internally. 2. Using create before destroy for safer updates. When updating resources like security groups or IAM roles, Terraform might try to destroy and recreate them. To avoid downtime or failure, you can use Lifecycle. Use when you want to ensure the new resource is created before the old one is destroyed. 3. Using ignore changes to avoid unnecessary diffs. Sometimes updates fail because Terraform tries to change something that should be left alone, like an externally managed field. Lifecycle. Use when external systems modify the resource and Terraform shouldn't try to revert it. 48. Terraform Guide 4. Retry logic with null resource, and local exec for scripts or commands that need retries. You can manually implement a retry loop using null resource and shell scripting. Resource null resource retry example. Do curl, f example and ain. And break sleep 10 done, EOT use. When calling APIs or commands that are flaky and may need retries. 5. Using depends on for ordering to prevent race conditions. Sometimes resources fail because dependencies weren't fully created yet. Resource XEs, instance example. Use when you need strict ordering to avoid race conditions. 6. Use modules and outputs for better error handling. Organizing infrastructure into modules and using outputs helps break down large operations and isolate failures to smaller scopes, improving retry recovery. Limitations in war. No custom retry count or backoff control for individual resources, like retry attempts in AWS SDK. All failures in one resource can halt the entire plan, apply unless isolated. No native support for conditional retries. Use null resource as workaround. Best practices strategy. When to use built-in retries. Most AWS Azure, GCP. API operations 49. Terraform guide strategy. When to use created before destroy resource replacements without downtime. Ignore externally managed fields. Null resource retry loop scripting with retriable actions. Depends. Unenforced dependency. Order a colleague accidentally deletes the Terraform state file. How would you recover and ensure no resources are recreated? Step-by-step recovery plan 1. Check for backups if you're using remote backends like S3 with Dynamob. OS3 usually has versioning enabled, so you can restore a previous version. Or go to the S3 bucket, Select Terraform TF state, click Versions. Restore the latest known good version. Dalton Town, Cloud or Enterprise. Oh, they maintain state history. You can roll back from the Terraform UI. With no backups exist too. Use Terraform import to rebuild the state. You must manually re-import all existing resources into a new Terraform state file. This avoids recreating them. Example. Suppose you had an AWS EC2 instance and security group. Terraform import AWS instance. Web I 0 beast 12.3 300 45 def 67,000 1890. Terraform import AWS security group bot G SG 0 1 2 3 4 5 6 7 8 9 ABC def 0. This tells Terraform. This real AWS resource maps to this Terraform resource block. Make sure the main TF, or equivalent, file matches the actual configuration of those resources. Terraform Guide 3. Run Terraform plan to confirm no changes after importing all resources. Terraform plan if done correctly. Terraform should show no changes. If it shows a destroy create action something doesn't match, fix the configuration or import. 4. Recreate state file. Terraform TF state. Once you've imported all resources correctly, a fresh Terraform TF state is generated. You can now push it to your remote backend again, if applicable. Lock it using backend support like S3 plus DynamoDB. What not to do: don't immediately run Terraform apply after deleting state. It will try to recreate all resources. Don't manually edit the TF state unless you know exactly what you're doing. Prevention tips: always enable remote backends like S3 plus DynamoDB for locking and versioning. Use Terraform Cloud to store and version state safely. I'll consider automating state backups in a CI/CD pipeline. What is the purpose of Terraform's null resource, and when would you use it? Give an example code. The null resource in Terraform is used to execute arbitrary actions that are not directly associated with any specific cloud provider resource. It's a resource placeholder that allows you to run provisioners, for example local exec, remote exec, when no other suitable resource exists, or when you want to create custom behavior during apply. Time. Listada. Nashadian. Key use cases for null resource. 1. Running local or remote scripts. 2. Performing configuration steps outside Terraform's built-in resources. 3. Triggering actions based on changes in input variables using triggers. 4. Debugging or prototyping Terraform logic. 51. Terraform guide example. Using null resource to run a shell script resource null resource. Run script triggers, UA hash forces this to rerun on every apply explanation. Local exec tells Terraform to run the command on the machine where Terraform apply is executed. Ooh. The triggers block is used to specify conditions under which the null resource should be recreated. Using timestamp ensures it always runs. When not to use it. Avoid overusing null resource for tasks that can be better modeled with proper Terraform providers, like using a AWS instance instead of using a null resource to run an AWS 151 command. How can you perform targeted resource deployment in Terraform? Can you give one example? In Terraform, targeted resource deployment is achieved using the target option with the Terraform apply or Terraform plan commands. This allows you to apply changes only to a specific resource or module, instead of running a full deployment for all resources. Syntax. Terraform apply, target resource type, bit resource name. Or for a resource inside a module. Terraform apply, target module, done a module named or resource type. Bet resource, name example. Suppose you have the following resources. Resource use 3 bucket my bucket. 52. Terraform guide resource instance. NEST dual. If you want to apply only the S3 bucket creation and skip the ET2 instance for now, Terraform apply. Target cause S3. Bucket, dent, and bucket notes. Useful during debugging, testing, or partial deployments. All does not guarantee dependency completeness. Terraform will still attempt to evaluate dependencies. Use sparingly in production, as it can lead to configuration drift if not used carefully. Project structure, WGIMANTF, G, modules, J, S, S3.tf modules, S3 bucket, S3.tf, resource S3 bucket. This variable bucket name, main.tf, module, S3, bucket module. Resource targeted. Edge to targeted. Deployment example. 53. Terraform guide if you only want to deploy the S3 bucket inside the module. Terraform apply. Target module.s3. Bucket module. Or to target the specific resource within the module. Terraform apply. Target module-3. Bucket module. You only want to update one part of your infrastructure without affecting the rest. You're troubleshooting or validating the behavior of a specific resource module. Tell me 5 scenarios where Terraform apply will pass. But when you run Terraform destroy, it will fail. Here are 5 scenarios where Terraform apply might pass, but Terraform destroy could fail. 1. Manual changes to resources. If manual changes are made to resources outside of Terraform, for example, directly in the AWS console, Azure portal, etc., Terraform may no longer have an accurate view of the state. When you run Terraform destroy, Terraform could fail to destroy the resources because the actual state doesn't match what Terraform expects. 2. Resource dependencies or deletion order. Terraform applies resources in a specific order based on their dependencies. If a resource is dependent on another, Terraform will destroy them in reverse order. However, if there is an external dependency or a resource that is locked or in use, for example, an EC2 instance that's running or an RDS instance with active connections, the destroy operation might fail. 3. Provisioned resources with external constraints. Resources that have external constraints, like security groups, IAM roles, or databases, may fail to be destroyed if they are still in use or have dependencies not defined in Terraform. For example, an RDS instance may have an active connection or a security group might still be attached to another resource, causing the destroy operation to fail. 4. Immutable resources. Certain resources like managed services, for example, AWS RDs or AWS Redshift clusters, might have configuration constraints that make them immutable once created. Even though Terraform apply might succeed when initially creating them, running Terraform destroy might fail because these resources cannot be easily destroyed or replaced due to their immutability, or because certain parameters can't be reverted to the required state. 5. State corruption or mismatched state files. If the Terraform state file becomes corrupted or is out of sync with the actual resources, for example, if it's been manually edited, or if the state file was not properly updated during an apply, Terraform may successfully apply changes but fail to destroy resources because the state does not reflect the current infrastructure. This can happen when you have multiple people working on the same state file, or if state management, for example via remote backends, is not set up properly. Terraform Guide 1. Resource dependency or missing dependencies. A scenario. Resources that were created by Terraform depend on other resources not managed by Terraform. For example, external resources or manual changes to the environment. Joe, what happens? Terraform apply can create the resources as it doesn't check for external dependencies. However, when you try to run Terraform destroy, Terraform fails to delete those resources because they are dependent on something outside of its control, like external service dependencies or missing permissions. 2. Manual modifications outside Terraform. Scenario: if a resource was manually altered outside Terraform, for example, a resource in AWS was modified directly through the console, Terraform might not be aware of the change. What happens? Terraform apply will create resources based on the current state. But when it attempts to destroy the resources, it fails because Terraform tries to remove the resource that was modified in a way that doesn't match the Terraform state, like a different tag, name, or security settings. 3. Resource with protection, deletion policies. Scenario: some cloud providers, like AWS or Azure, allow you to apply deletion protection, or set specific policies that prevent resource destruction. For example, the AWS instance with delete protection, true. What happens? During Terraform apply, the resource is created without issue. But Terraform destroy will fail if deletion protection or a similar safeguard is in place, preventing the resource from being deleted. 4. Orphaned resources not managed by Terraform. Scenario: resources such as networks, volumes, or IAM roles might have been created by Terraform but have orphaned components, like child resources, that aren't in Terraform state. What happens? Terraform apply successfully creates the resource, but when running Terraform destroy, it may fail because Terraform doesn't recognize or track the orphaned child resources, and thus cannot destroy them. 5. Insufficient permissions for deletion. Scenario: Terraform's execution role may have permissions to create resources but may not have sufficient permissions to delete them, for example, lacking the necessary IAM permissions to delete a security group or an EC2 instance. 1. What happens? The Terraform apply will succeed as it creates the resources with the available permissions. But Terraform destroy fails, because Terraform cannot delete the resource, due to missing permissions or access restrictions. 55. Terraform Guide 1. Resource dependency or missing dependencies real-time example. Scenario: you use Terraform to create an Amazon RDS instance with a VPC that was manually created before. The RDS instance relies on this manually created VPC. What happens? Terraform apply runs successfully, creating the RDS instance. Terraform destroy fails because Terraform doesn't manage the manually created VPC, and it cannot delete the dependent RDS instance. 2. Manual modifications outside Terraform. Real-time example. Scenario: you deploy an AWS E2 instance using Terraform. Later, you manually modify the instance by enabling termination protection from the AWS console. What happens? Terraform apply successfully creates the EC2 instance. Terraform destroy fails because termination protection prevents Terraform from deleting the EC2 instance. 3. Resource with protection. Deletion policies real-time example. You create an AWS S3 bucket via Terraform. After the creation, you manually enable S3 versioning or lifecycle policies outside Terraform. What happens? Terraform apply successfully creates the S3 bucket. Terraform destroy fails because the lifecycle policies or versioning settings prevent the bucket from being deleted without manual intervention. 4. Orphaned resources not managed by Terraform real-time example. You use Terraform to create an AWS load balancer, ELB, and security groups. Later, you manually add EC2 instances in the AWS console to be attached to the ELB, but do not manage these instances with Terraform. What happens? Terraform apply successfully creates the ELB and security groups. Terraform destroy fails because the EC2 instances added manually are not managed by Terraform and are not removed when destroying the ELB. 5. Insufficient permissions for deletion 56. Terraform Guide Real-Time Example. Scenario. You deploy AWS resources, such as IAM roles and security groups, using a Terraform service account that has only create permissions for certain resources, but lacks delete permissions. What happens? Terraform apply successfully creates the IAM roles and security groups. Terraform destroy fails because the service account doesn't have sufficient permissions to delete those resources, resulting in an error message about insufficient permissions. What are Terraform locals? Terraform locals are used to define values that can be reused throughout your configuration within a module. They are essentially variables that help simplify code by storing values that don't need to be passed in as input or output. Locals are evaluated once, and then can be used multiple times in the configuration. Locals allow for better readability, reusability and maintainability of your Terraform code, especially in larger projects. Syntax. Locals. You can use locals to store values like strings, numbers, maps, or lists. Real-time examples of Terraform locals. 1. Using locals to avoid repetition. Scenario. You have multiple resources that need to use a specific region, which might change based on environment. For example, US East 1, US West 2. Example. Locals resource AWS instance. Example 57. Terraform guide, resource EWS S3 bucket. Example in this example. The region local is defined once and used in both the EC2 instance and the S3 bucket resource. If the region needs to change, for example, for different environments, you can just modify the local, and it will be applied across all resources that use it. 2. Using locals for complex calculation scenario. You need to calculate some complex values like subnet CIDR blocks based on a network size. Example. Locals resource AWS US subnet example here. Local to subnet CIDR is calculated using the CIDR subnet function, which is a local expression based on a given base network and subnet mask. This allows for easy management of network ranges, as any changes to the base network or mask are automatically reflected in all calculations using local subnet CIDR. 3. Using locals with conditional logic scenario. You want to conditionally set values based on environment or other conditions. Example. Locals 58. Terraform guide resource instance example in this case. A local instance type is set to T2 large if the environment is production and T2 micro otherwise. This allows for different configurations for different environments, reducing redundancy in your code. 4. Using locals for lists and maps. Scenario. You want to store a list of tags and use them in multiple places. Example. Locals resource AWS instance example. Resource 3 bucket example here. The common tags local is used for both the EC2 instance and the S3 bucket, ensuring consistency in tags across resources. If you need to add more tags, you can update the local, and it will apply to all resources using local common tags. Key benefits of using locals. Reusability. Locals allow you to reuse the same value or calculation in multiple places. Simplification. Helps make your configuration more readable and maintainable. Avoiding repetition. Reduces the need to repeat the same expressions or values multiple times. 59. Terraform guide. Dynamic configurations. Supports complex logic or calculations that are needed for configurations. When to use locals. When you need to use a value multiple times in your Terraform configuration. When you want to simplify expressions and calculations in your code. When you need a dynamic value based on other resources or variables that don't require user input. In real-time projects, Terraform locals can make managing infrastructure configurations easier. especially when dealing with multiple environments, complex resource configurations, or dynamic calculations. How to set up Terraform CI/CD and best practices. Setting up Terraform CI/CD pipelines using Jenkins and GitHub Actions is a great way to automate your infrastructure provisioning and management. Below are detailed steps and best practices for configuring CI/CD with both Jenkins and GitHub Actions. 1. Terraform CI/CD setup with Jenkins prerequisites, Jenkins installed and running. GitHub repository containing your Terraform code. AWS credentials or credentials for your cloud provider, set up on Jenkins. Steps. Step 1. Install required Jenkins plugins. GitHub plugin. To connect Jenkins with your GitHub repository. Terraform plugin provides support for Terraform commands, for example, plan, apply, etc. Pipeline plugin. To define Jenkins pipelines. Step 2. Create a Jenkins pipeline 1. Go to Jenkins and create a new pipeline job. 2. Under pipeline configuration, choose pipeline script from SCM. 3. Select Git as the SCM type and configure it with your GitHub repository URL. 4. In the branch field, set the branch you want to track, for example, main. 5. Define the pipeline script in the Jenkins file, located in your repo or directly within Jenkins. Jenkins file example, pipeline agent any60. Terraform guide environment stages stage, Terraform init, O, stage. Terraform validate, O stage. Terraform plan, stage. Terraform apply, stage. Terraform destroy. Terraform guide steps, underpost, or Jenkins pipeline breakdown. Checkout code. Pulls the Terraform code from your GitHub repository. Terraform init. Initializes the working directory and configures the backend. Terraform validate. Ensures the Terraform code is valid and ready to execute. Terraform plan. Runs Terraform plan to generate an execution plan. Terraform apply. Waits for manual approval to apply the plan. Good practice to avoid accidental deployments. Terraform destroy. Optionally, it destroys the resources after tests or when tearing down environments. Step 3. Configure Jenkins credentials EU. Store AWS credentials or other sensitive values securely in Jenkins using Jenkins Credentials Store. Reference the credentials in the pipeline using AWS access key. Credentials, access key, AWS key, AWS secret, credentials, AWS secret, access key. 2. Terraform CD setup with GitHub Actions, prerequisites, GitHub repository containing your Terraform code, Joel AWS credentials or credentials for your cloud provider set up in GitHub Actions. Steps. Step 1. Create a GitHub Actions workflow, 62. Terraform Guide 1. In your GitHub repository, go to the Actions tab. 2. Create a new workflow by clicking New Workflow and selecting Set up a workflow yourself. 3. Create a GitHub Workflows Terraform .iml file. GitHub Actions workflow example. Name, Terraform sit cd on. Push, branches, main pulled request, branches. Main jobs, Terraform, runs on, Ubuntu latest environment, AWS region, US West 2 steps. Name, checkout code uses, actions checkout at v2. Name. Setup Terraform uses, HashiCorp setup Terraform at 1 with, Terraform version 1.60. Name. Configure AWS credentials uses. AWS actions. Configure AWS credentials at 1 with. AWS access key. $double WA6 access. $1 $. $form init run. Terraform init run. Name: Terraform validate run. Terraform validate name: Terraform plan run. Terraform plan out RTFS plan 63. Terraform guide name: Terraform apply run. Terraform apply auto approve TF plan if GitHub event name push. Name: Terraform destroy run. Terraform destroy auto approve if GitHub events name push and GitHub or refs heads. Main GitHub actions workflow breakdown. Checkout code checks out the Terraform code from your GitHub repository. All setup Terraform uses the HashiCorp setup Terraform action to install the specified Terraform version. Configure AWS credentials uses AWS actions. Configure AWS credentials to authenticate with AWS using secrets stored in GitHub. Terraform init initializes Terraform and sets up the backend. Terraform validate validates the Terraform configuration files. Or Terraform plan runs Terraform plan to generate an execution plan. Terraform apply applies the Terraform plan if the action is triggered by a push event. Joel Terraform destroy. Optionally, you can add a step to destroy resources after the deployment is complete. Step 2. Store secrets in GitHub to store sensitive values such as AWS credentials in GitHub secrets for secure access in the workflow. Go to your GitHub repository, navigate to Settings eSecrets, and add AWS access key. Edit AWS secret access key. Step 3. Trigger workflow. The workflow is triggered on push and pull request events to the main branch. You can modify the workflow to trigger on other branches or events as needed. Best practices for Terraform CI/CD, Jenkins and GitHub Actions. 1. Use remote backends for state management. Jenkins. Store the Terraform state in a remote backend such as S3 with DynamoDB for state locking. GitHub Actions. Use Terraform Cloud or S3 with DynamoDB to manage the state remotely and prevent conflicts with state files. 2. Manual approval for Terraform apply bshachu and seed as a manual approval for Terraform apply. Avoid automating Terraform apply directly for production resources. Always require manual approval before applying changes to production. 64. Terraform guide Jenkins. Use an input step for manual approval. All GitHub Actions. Use workflow dispatch or similar methods for manual approvals. 3. Store secrets securely. WASH. Use GitHub secrets in GitHub Actions or the Jenkins credentials. Store to store sensitive values such as AWS credentials. 4. Separate plan and apply steps. Separate the Terraform plan and Terraform apply stages. This allows teams to review the plan before applying changes, minimizing errors. 5. Testing and validation. Implement Terratest or Kitchen Terraform for testing Terraform code and resources. Or run Terraform validate in sitcd to catch syntax or configuration issues before deployment. 6. Use modules for reusability. Organize your Terraform code into modules to promote reuse and better organization. Share common infrastructure components. For example, VPC, IAM roles, EC2 instances, as reusable modules in your pipeline. 7. Isolate environments. Use Terraform workspaces or separate configurations for different environments, for example, dev, prod staging, to isolate state and configuration. 8. Clean up after tests. Seawall. Set up a Terraform destroy stage to clean up resources, especially in testing environments, to prevent resource sprawl and unnecessary costs. 9. Use linting and formatting. Integrate Terraform FMT and Terraform validate in your pipeline to ensure your code follows best practices and is correctly formatted. Conclusion: by combining Jenkins and GitHub Actions with best practices for Terraform CCD, you can effectively automate your infrastructure deployment and management processes. Use manual approvals for critical steps like Terraform apply and leverage remote backends for state management to prevent conflicts. Always store credentials securely, and ensure that your infrastructure is tested and validated throughout the pipeline. 65. Terraform Guide. What are dynamic blocks in Terraform, and what are the best practices? In Terraform, dynamic blocks allow you to create resource configurations or modules dynamically based on a variable or a list of values. This is useful when you need to generate multiple instances of a resource block based on some input data. What are dynamic blocks? Dynamic blocks allow you to generate repetitive sections of Terraform code. Instead of manually defining each block for each resource, a dynamic block can loop over a list of values, or any other structure, to create those blocks. Syntax of a dynamic block. A dynamic block has the following syntax. Dynamic block type uBlock type. The name of the block you want to generate dynamically. For example, security group, rule, ingress, egress. Or fetch. A list or map that defines the number of instances to generate. All content. The block's contents, where you can reference values from the for each expression. Example of a dynamic block. Consider a scenario where you're provisioning an AWS security group and you want to create multiple ingress rules dynamically. Variable ingress rules. Default H8. 66. Terraform Guide. Resource EUS security group example. In the example above, the ingress rules variable holds a list of objects containing CIDR, port, and protocol. The dynamic ingress block loops over the ingress rules variable and creates a security group rule for each entry. Real-world use cases for dynamic blocks. 1. Security group rules. As shown in the example above, dynamic blocks are often used to create multiple ingress or egress rules based on a list of objects or values. 2. Cloud instance tags. If you want to dynamically assign tags to instances based on environment or other parameters, you can use dynamic blocks to create multiple tags. 3. Load balancer listeners. If you want to dynamically define multiple listeners for a load balancer. For example, HTTP, HTTPS. Dynamic blocks can loop through a list of protocols and ports. 4. Auto-scaling group launch configuration. If you want to define multiple block types for the launch configuration, such as environment variables or block device mappings, dynamic blocks can generate those based on input values. Best practices for using dynamic blocks in Terraform. 1. Use dynamic blocks for complex or variable configurations. Dynamic blocks should be used when the number or configuration of the block types is dynamic or variable. For example, when the number of security group rules is determined at runtime by a variable or list. 2. Avoid overuse of dynamic blocks. While dynamic blocks are powerful, they can make your Terraform code harder to read and maintain. Avoid using them for simple static configurations where you could just define the block directly. 67. Terraform Guide 3. Leverage variables for flexibility. To make the dynamic block flexible, define the values to loop over as variables. This allows your code to be reusable and modular across different environments or configurations. 4. Validate input data. When using dynamic blocks with variables, for example lists or maps, make sure to validate input data to avoid runtime errors. You can use type constraints and validation rules in your variables to ensure that data passed into the dynamic block is in the expected format. 5. Avoid complex logic inside dynamic blocks. Keep the logic inside dynamic blocks simple. Complex logic can reduce readability and maintainability. If you need complex operations, try to handle them outside the dynamic block using locals or other Terraform functions. 6. Document the dynamic block usage. Since dynamic blocks can generate multiple resources based on a list, it's essential to provide clear comments and documentation in your code to ensure other team members understand how the dynamic block works. 7. Use for each instead of count in dynamic blocks. In many cases, using for each is a better practice than count for dynamic blocks, especially when the data involves maps or complex objects, as for each makes it easier to refer to specific keys or elements. Example of dynamic block for multiple tags. Let's say you need to assign tags dynamically to an AWS EC2 instance. The tags are stored in a variable as a map, and you want to apply them dynamically. Variable tags. Egg resource instance example, NGZ868. Terraform guide in this example. The tags block is dynamically created based on the tags map variable. Each key value pair in the map results in a separate tags block being created. Summary of key points of dynamic blocks. Help automate and simplify resource creation when dealing with repeating blocks based on data structures like lists and maps. Best practices. Use dynamic blocks for complex and variable configurations. Avoid overuse. Validate input data, and keep logic simple. Common use cases. Security group rules, tags, load balancer listeners, and auto-scaling configurations are some common examples. By using dynamic blocks, you can reduce code duplication and improve the maintainability of your Terraform configurations. What is Terraform drift and best practices to manage it? Terraform drift refers to a situation where the actual state of your infrastructure diverges from the state managed by Terraform. This typically occurs when resources are modified or changed outside of Terraform, for example, manually from the cloud provider's console or through other tools. As a result, Terraform's state no longer accurately represents the real-world configuration of resources. Terraform drift can occur for various reasons, such as manual changes. A user manually updates the configuration of an infrastructure resource outside of Terraform. Automatic updates. Cloud providers or other systems automatically modify resources, for example. Scaling. Updates to managed services. External systems. Other automation tools or CI/CD pipelines may modify the resources. Drift can lead to issues when you run Terraform plan or Terraform apply, because Terraform may try to reapply or revert changes to align resources with the defined configuration, causing potential conflicts or errors. Why does Terraform drift matter? 1. Inconsistency. Terraform cannot manage resources that have been changed manually, causing confusion and lack of alignment. 2. Loss of control. Manual changes mean the desired state described in the Terraform configuration is not reflected in reality. 3. Risk of overwriting. If drift is not detected, Terraform could overwrite the manual changes made to a resource, leading to unintended consequences. How to detect and manage drift 69. Terraform Guide 1. Detecting drift in Terraform. Terraform does not automatically detect drift, but you can manually check for it using the following methods. Using Terraform plan. Run Terraform plan to compare your current infrastructure state with the state defined in your Terraform configuration. This will show you any differences. Terraform plan. If any drift has occurred, Terraform will detect the differences and show what it intends to change. Using Terraform refresh. You can run Terraform refresh to update the state file with the latest state of the infrastructure. Terraform refresh. This will sync your Terraform state with the actual state of the infrastructure. However, this does not fix drift. It only updates Terraform's state file. Third-party tools. There are tools like Terraform drift detection that scan your cloud environment and check for drift across resources. 2. Managing drift. Once drift has been detected, you have several options for managing it. A manual intervention. Inspect and correct drift. Review the drift and either manually revert the changes in the cloud provider's console, or use Terraform to bring the infrastructure back to the desired state. If changes were intentional, for example, for scaling or urgent fixes, you can update your Terraform configuration to match the new reality and prevent future drift. If changes were not intentional, Use Terraform to realign the resource with the desired state. B. Reapply Terraform state. After detecting drift, you can apply the changes from Terraform to correct the infrastructure back to the defined configuration by running Terraform apply. This will reconcile the differences between the actual state and the desired configuration. C. Update your Terraform configuration 70. Terraform Guide. If drift occurred due to missing changes in your Terraform configuration, you can modify the Terraform code to match the actual state, and then apply the changes. De-enable state locking when multiple teams or automation tools are interacting with Terraform. Ensure state locking is enabled to prevent concurrent modifications that could cause drift. For example, if using WSS3 as a backend, enable state locking with dynamodb. Terraform G. This ensures that only one process can modify the state at a time. Best practices for managing Terraform drift. 1. Version control and code review. Store Terraform configurations in version control. Ensure all your Terraform code is stored in version control, for example Git. This enables you to track changes and catch potential drift issues caused by unapproved changes. Code review process. Implement a code review process for all changes to your Terraform configuration. This can help prevent unauthorized or manual changes to infrastructure. 2. Enforce immutable infrastructure. Immutable infrastructure. One of the key principles of infrastructure as code, IAC, is the idea of immutable infrastructure, where resources should not be manually modified once they are created. Instead of making changes manually, any required changes should be done through Terraform. UN. Automate rollbacks. If manual changes need to be applied, they should be tracked, and changes should be rolled back through automation tools, rather than manual intervention. 3. Use Terraform Cloud. Enterprise Centralized State Management. Terraform Cloud or Terraform Enterprise provides a centralized service for managing Terraform state and collaboration across teams. It includes features like state locking, drift detection, and notifications for drift. 71. Terraform Guide Policy as Code. Terraform Cloud Enterprise offers the ability to define policies that prevent unauthorized changes from being made outside of Terraform. This ensures that infrastructure is only managed by the defined Terraform configurations. 4. Regularly refresh Terraform state. Run Terraform refresh periodically to ensure your Terraform state is in sync with the actual infrastructure. This will help catch drift early and avoid surprises when running Terraform plan or Terraform apply. 5. Implement automated drift detection. Newton. Set up drift detection tools such as Terraform drift detection or third-party monitoring systems to periodically check for drift in your infrastructure. Some teams use external monitoring tools, for example, Datadog CloudWatch, to alert them when a resource's configuration changes unexpectedly. 6. Use immutable infrastructure patterns. Infrastructure as code with CI/CD. Build a CI/CD pipeline for Terraform that ensures your infrastructure is continuously tested and deployed, avoiding manual changes. When changes need to be applied, they go through the CI/CD pipeline, ensuring that they are tracked and versioned. Automate Terraform runs. Use a tool like Jenkins, GitLab CI, or GitHub Actions to trigger Terraform runs as part of your CI/CD pipeline, ensuring that your infrastructure is always aligned with your desired state. 7. Manage access to cloud providers. Restrict access. Ensure that only authorized users or systems can make manual changes to infrastructure. Use tools like IAM policies, service accounts and roles to limit manual access to critical resources. Summary. Terraform drift occurs when changes are made to your infrastructure outside of Terraform, causing a mismatch between the actual state and the state managed by Terraform. To manage drift effectively, use a Terraform plan and Terraform refresh to detect drift. Will regularly refresh your Terraform state. Apply best practices like version control, immutable infrastructure, and automated drift detection. Use tools like Terraform Cloud Enterprise to centralize state management and prevent manual changes. 72. Terraform Guide. Explain different types of dependencies in Terraform. In Terraform, dependencies are critical for ensuring that resources are created, updated, or destroyed in the correct order. Terraform has built-in mechanisms for managing dependencies between resources, both implicitly and explicitly. Understanding the different types of dependencies in Terraform helps you control the flow of resource creation and modification. Types of dependencies in Terraform. 1. Implicit dependencies. 2. Explicit dependencies. 3. Data source dependencies. 4. Provisioner dependencies. 5. Module dependencies. 1. Implicit dependencies. Implicit dependencies are automatically created by Terraform when one resource refers to another. This means Terraform understands that one resource needs to be created before another because of the reference between them. GU. How it works. When one resource refers to the output of another resource, such as using the ID of a resource, Terraform automatically establishes an implicit dependency. Example. In this example, the AWS security group resource depends on the creation of an AWS VPC because the security group references the VPC ID. Resource database VPC example. Resource AWS security group. Example here. The security group implicitly depends on the VPC because it uses the VPC AWS DC. Example. Terraform will automatically create the VPC first and then the security group. 2. Explicit dependencies. Explicit dependencies are defined using the depends on argument, which allows you to manually specify the order in which resources should be created, updated, or destroyed. While Terraform generally handles the dependency graph automatically, the depends argument is useful when implicit relationships are not enough, or when you need to enforce a specific order of execution. 73. Terraform Guide. How it works. You explicitly tell Terraform that one resource depends on another, ensuring that the dependent resource is processed first. Example. In this example, the AWS security group explicitly depends on the AWS EBC and AWS instance resources being created first. Resource AWS VPC. Example. Resource instance. Example. AWS security group. Example. Here the AWS security group at example depends on both the AWS VPC AWS instance, and it depends and ensures the security group is created after both resources. 3. Data source dependencies. In Terraform, data sources allow you to fetch data from an external system, for example from AWS, Google Cloud, etc., without creating or managing resources in the state. Data sources often introduce dependencies because the data retrieved can be used to configure other resources. How it works. If a resource references a data source, an implicit dependency is established on the data source. Example. Here, the AWS security group references a data source to find an existing security group, creating an implicit dependency. Data was security group existing resource. AO was instance. Example. Terraform Guide. In this case, the AWS instance.example depends on the AWS security group existing data source, meaning the data source is queried before the instance is created. 4. Provisioner dependencies. Provisioners are used to execute scripts or commands on a resource after it has been created or updated. While provisioners are not recommended for general use, as they can create dependencies that Terraform cannot track, they can create implicit dependencies, especially when they execute actions based on resource creation. How it works. The provisioners often create dependencies on other resources because the commands might depend on data or state from other resources. Example. Here, a provisioner depends on an instance being created to run a script. Resource AWS instance. Example. In this case, The provisioner depends on the AWS instance. Example being created first before running the script. 5. Module dependencies. When you use modules in Terraform, dependencies can be established between different modules. This is particularly useful for organizing large configurations, where one module's output may be another module's input. Wow! How it works? Modules have outputs that can be passed as inputs to other modules, creating an explicit dependency. Example. Here, a VPC module is used in one module, and the output from that VPC is passed into another module, for example, to create instances in the VPC. 75. Terraform Guide, Module VPC. Module instances. In this case, the instances module explicitly depends on the VPC module because it needs the VPC output to create the instances inside the VPC. Best practices for managing dependencies in Terraform. 1. Use implicit dependencies. Let Terraform automatically handle dependencies whenever possible. Terraform's built-in understanding of resource dependencies usually results in a cleaner and more maintainable configuration. 2. Use depends on sparingly. Explicit dependencies using depends on should be used only when Terraform cannot automatically infer the correct order. Overusing depends can make your code more complex and harder to maintain. 3. Avoid manual changes. Try to avoid manually changing infrastructure that is managed by Terraform. Manual changes can break the implicit dependencies Terraform creates. 4. Modules for reusability. Leverage modules to encapsulate reusable logic and pass values between modules explicitly. This helps maintain clear dependencies and improves the modularity of your Terraform configuration. 5. Use data sources wisely. When using data sources, make sure to handle dependencies correctly. Since data sources are often used to retrieve external data, they may create an implicit dependency chain. 6. Limit provisioner usage. Provisioners are often not ideal for creating dependencies. They can cause issues in managing state and should only be used in cases where it's absolutely necessary. For example, bootstrapping a system. Summary. Terraform manages dependencies using both implicit and explicit methods. Implicit dependencies are automatically handled when resources reference each other, while explicit dependencies are manually defined using depends on. Additionally, dependencies can exist in data sources, provisioners, and modules. By understanding and managing these dependencies effectively, you can ensure that your Terraform configurations are more reliable, maintainable, and scalable. Connect with me. Sidhu 14376